For the video, I'm Gašper Ažman.
Hey.
Hi, Gašper.
Hello. I'll be talking about supposedly functional C++ today. And this word means something very different to me than to most people, I bet. So let's start with some legal disclaimers, because I work for CppNow, and they're a finance firm, and they paid for me to do this during my work time because I was building an actual production thing with this thing. So I'm really grateful for them for taking the chance on something completely wacky like this. That said, this is not investment advice. None of this text is endorsed by them, and my words are my own. So, you know, sue me if it goes wrong, not them. Right, so other disclaimers. This is slide code. This is supposed to be an interactive talk, but don't heckle me about missing no except. That's not the point. If it's not there, it didn't fit on the slide, right? I've omitted a lot of stuff, like no except propagations, finite correctness, nicer errors, almost all of the meta programming. I'll have a few tidbits just for the people who find this boring. Compile time optimizations, lots of niceness, automatic inference, some of it, and tons of other stuff. Like I'm going to be talking about the meat, not the nice. Exactly, unlike Zach, who mostly talked about the nice bits. Okay, so C++ is not made for this, okay? I have proposals that are going to make it slightly better. Those are them. This is not a list that is sufficient, but it does make things better. The errors are bad, okay? Like we're doing something wacky. The compile times are worse. But getting better, like with papers, things will improve. That's why there's papers. The runtime performance is actually pretty great. As I said, I did this for an actual production system. It worked super well. And yeah, something alias analysis, right? It turns out if you give the compiler a lot of information, it knows what to do with it. When in doubt, do this simple thing. Like what I'm talking about pays off in the large. Like if you're doing some core kernel or whatever, like don't listen to this. This is not the area of application for this stuff, right? The library is open source, thanks to Brone Kuzicki. And Alex Bartosz Milewski helped with the category theory, and Lisa helped with the rest today. And I will probably have to write a paper on that because it's so cool. Right. It is highly experimental, like the open source one. The closed source one that we have, as I said, used in production, worked really well. But this one's better because we learned things, right? The point of why we want to do this is we want to optimize for correctness first. The reason we built this was because we were building a crypto trading stack. And it turns out the wonderful world of crypto exchanges is written in Node.js. And so that means that it's awful. Like, we wanted to be damn sure that when something goes wrong, it ain't us. Okay? So we wanted to be correct by construction in C++. So we wanted to let the compiler prove our code. And we said, only plausible business logic should compile. This is like a wider set than correct, but it is a much slimmer set than the usual thing we're working with in C++. We said tests are CRCs for our proofs. When you're writing an algorithm, you are already proving your code in your head, otherwise it wouldn't work. Now, you might be wrong about the proof, but that's what you're trying to do. When you're writing tests, you're writing a CRC for that proof you did in your head. The more of that proof you encode in the type system, the less you have to do in your head. So yeah, proofs are hard. Our brains are decidedly not. So we always talk about how to break down problems into smaller problems, but this is about how we break down solutions, okay? And thank you, Tony. Context is the greatest complectifier of proof, right? The less context you have, the easier it gets. Yeah, we usually do this. The context of a line of code, just to convince you that this actually matters, you have explicit context, like local variables, function arguments. Your object has state, and that state changes, but that's relatively close by. So that's why I'm calling it the explicit context. There's also block context, like you've got your loop conditions, like that are true within the loop. You've got the loop post condition, which is some kind of an inverse of your loop condition because you got out, right? The current and closing if conditions, the negatives of the previous if conditions who you are in the else block of. If you're in a catch block, are you within a for loop and processing a sequence? That's all part of the block context. There's more implicit context. You've got global variables, thread local variables, syscall accessible stuff that you need to keep in mind, right? Environment variables, file system GUIs, like there's network resources. You thought I was done. There's the current exception. Thank you, Lisa, for your wonderful lipping functions. May we all hate them forever. Which exceptions may be thrown by your subcalls. This is implicit because we don't write it out. Cursors of open files. Those are global variables, guys. Open sockets and connections. Those are shared resources in a flat namespace. Shared memory regions, which are the same. You thought I was done. Dispatched async operations and how to cancel them. Operating system limits, which are, again, a global thing. Global subsystems, which we all know and love. Some of them more innocuous than others. You thought I was done. State machines, which state are you in? Sometimes that's implicit in the name of the function that got called, and you just know that that other state machine is in that other state. Which execution context is running your code? Some code can only be run in real-time context. Some absolutely cannot and should not be ever run in real-time context. Some code, is the top half of a signal handler, and you need to know that. And so for every context, there grows a monad. This is a really terrible paraphrasing of one of my formative childhood movies. It has this wonderful character, Teta Pechta, who's a herbalist. And she said, for every disease, there grows a flower. She was terribly wise and very cranky. All right. When I say monad here, I really mean a compositional context. I will be talking very loosely. Don't at me. Composition is what we're trying to understand here. Functor, applicative, monad, all of the other things, I'm just glossing over that. If you want to know exactly what things are, talk to Ben and Connor, who is not here. I'm throwing you under the bus, Ben. All right. We're also going to be implicitly talking about indexed monads and graded monads, and I might mention those things. You do not need to understand what they are. So we want to limit context because most of it is irrelevant at any one time because otherwise code wouldn't work, right? Like we make that happen. We decomplectify code to the point where this is true. Which is why that's up to convention and discipline. Turns out that humans are hard to corral, especially if they're software engineers, because they think they know what they're doing. And so the core reason we even reach for functional approaches is that procedural languages have problems encoding proofs about context. They have a lot of power encoding proofs about all kinds of other things. Context is the devil. But in functional languages, right, all context is explicit, which helps proofs. So can we be disciplined in C++ to do this? And we will need tools, right? Like the answer is no, we can't, but maybe we can learn. Yeah.
You say all context is explicit. You were mentioning some OS-specific stuff. Number of total file descriptors opened can't possibly be explicit in the language.
That is true, but you can encode that in your specific I/O monad that you might be using, right? Like you can track that if you really need to. Like you can make it explicit.
It's kind of asynchronous, and the answer you get is outdated by the time you get it.
You're not
sort
allowed
of.
to ask. You're not allowed to ask how the I/O monad works. Is the answer there?
Yeah. Like yes, there are some things that are very difficult to encode to the point where it's not useful, right? Like I'm not saying go all the way pure functional. I'm saying limit context as much as possible. I'm trying to give you tools to do that to the point where it makes sense. Yes, Lisa.
Yeah, I want to point out that that wasn't a functional example. That was a functional grafted onto procedural example because the file system isn't acting functionally there.
True. But we are in a procedural language trying to do functional programming, and I'm not throwing that away. I'm giving you an extra set of tools, right? So we want to banish all context accessors from business logic into name contexts. And we will explicitly give access, and we will be free. Thank you, Tony. But master, my function now has 43 parameters. You were blind, but now you see, right? We need to design for laziness. We need to make the wrong things painful. This is the other part of the pit of success. The wall has to be high, right? Otherwise, you have a really big problem corralling the rest of your org to do the right thing. And if you have to pass 43 parameters, perhaps you will engineer your program so that you don't have to, right? That means you push control flow into context or up. You push mutation up. This is exactly what Tony said with separate compute and calculating and doing. That's exactly push stuff up towards main. I don't mean into main. That's too far. But like there's a delineation between where stuff happens and where stuff is calculated, and like push that up as possible, right? Because that means it's easier to reason about your program, not other reasons. Yes, thank you for that talk. Flat is better than nested. This is where that comes from. Have you considered flattening out your dependencies, right? So I'm going to go through a few classic monads here just to like give you an overview of the tools that we usually use for this. We use the maybe monad, which we call optional. We use the error monad, which we call expected, and it's got the types the wrong way around. Which is why it's so weird to say we've got T on the right, it's on the left actually. For us, it's fine. I'm hopefully not going to screw that one up. Stud ranges is effectively the elaborated list monad, or the family of, right? As we will see, optional is actually two monads, if you really want to be pedantic about it. The async monad is stud execution. We're actually building it into the language. I/O is the I/O resources part of stud execution. The state monad is, I mean, that's really well supported in C++. If you don't do the plop thing, as in the position being relevant for what your objects are, right? Like the small talk idea of object-oriented programming was effectively monads. Like true and false are how you do ifs, right? Like that's not about location, that's about functionality. That's also OOP, but different, right? The environment monad, async, like stud execution also has that. We don't expose it yet. Nobody's really programmed it. You don't need to know what it is. And the final guideline is we want to name common patterns and control flow. And why do we want to do that? We want to do this because bugs are on the intersections of proven code, right? It's when we put things that are proven together that we screw up the boundaries. That's where bugs happen. And so the bigger things you can name and have a proof for them, the easier it is to say, well, I at least know that this part of the program is correct. And so that's why giving something a name matters, right? Because it has a proof attached to it. It also makes it easier to use, but like that's why I'm like, okay, no raw loops, fine, thank you, Sean, but why though? Like, yes, rotate.
Yeah, it's a rotate.
But the point is the proof, right? The point is that those few lines of code that you wrote, you need to do the proof every time, but the proof for rotate is the proof for rotate. So I want to run through like optional to give everybody a taste who, doesn't do this all day, every day. Optional has two patterns of use. We have the short circuit pattern, which is optional plus the and then operation. So and then, this is a weird notation, right? What it says is, and then is a functional lift. It takes a function from t to optional of u. Notice u is not the same as t. And it gives you a function that goes from optional of t to optional of u. And then you can apply that function to your optional. The fact that there's a dot there is irrelevant. We use a pipe because we actually need the lift of and then also. So the point of and then is it's a lift that you give a normal function that you know what it does to, and then it translates it into the monad context. And then you can actually use it like a function because then you're not in the monad context morally anymore because it just does the thing. So the short circuiting pattern means this. Do we have anything? If we do, then we do the thing. Otherwise, we just say, well, there was nothing there, so we just return nothing. And this means that the first time you fail where there's nothing, then you just short circuit all the way to the end. That's the short circuiting pattern. That is the control flow encapsulated in the maybe monad, right? Turns out we do this a lot in programming because we want to like merge ways that we do things to make things flat. So if you have this pattern, consider using the maybe monad to give a hint to the reader that that is what you are doing. We name common patterns. As an example, we have a function parse URL. It returns an optional of a URL. We get the URL from the JSON file. It is an optional of string because you might not have the URL in there. And then we parse the URL, and then we do HTTP get. And we get an optional of HTTP result, right? So these are all different optionals. This is very easy, right? All of these return a maybe because they can fail, but if they fail, it's not considered catastrophic, right? We'll get to the exception, to the expected. The other pattern of optional, which is the other monad, which is like this one but upside down, is defaulting. We do this a lot too. If you are doing defaulting, consider using optional. It's just that the bind operation for this pattern is or else. So what does or else do? Well, it takes a function from nothing as an empty parameter list to optional of t and gives you a function from optional of t to optional of t. So if you already have something, that's what you get. If you have nothing, you call the function and it maybe succeeds and gives you something, or it'll still give you nothing. And this is why we can do defaulting with this compositional pattern. So this is the pattern. You have an optional. If there's nothing in it, you return the option. Sorry, if there's something in it, you return the optional. Otherwise, you call the function. Yes?
So you're calling these things lifts, right?
Yes.
And each lift picks up a branch prediction slot?
It is a lift in terms of it takes a function and returns a function.
Yeah.
implementation of the lift is a branch. But that's like fundamental to the maybe monad. It's not fundamental to all monads.
Got it. Okay, yeah.
Right? Like, so if you're using the maybe monad, that's what you wanted to do. You're not actually paying anything more. You're just making it easier to reason about your code.
I'm just comparing it to exceptions.
This is not exceptions.
I know. Go on. I'm interrupting.
Yeah. Thank you. No, please interrupt. Like that's good, right? But maybe is especially not exceptions. All right. So as another example for people who need to get some actual grips with this pattern, like let's try to do something like get hostname or whatever. Like we need to connect somewhere. We have several places we can get it from, and we'll just this is what we start with, right? This is not using optional. Like we have these two we have these two free functions, right? Like is hostname in args, get hostname from args. This is a very typical pattern. And then we've got this top level function that returns you a stud string. Notice it takes a default hostname in argc and argv and does the usual thing, like if the hostname is in args, then get it. Otherwise, get env service hostname. Yes, I love hidden parameters. Right? And then we have this extra thing that says, well, maybe this succeeded, but returned nil pointer. So that's fine, we have nothing. But maybe it returned an empty string because environment variables can be empty. And because people don't know how to unset them, we probably want to treat those as the same thing. And so then if both of these are untrue, then we actually have found our hostname. Otherwise, we return the default hostname, right? Okay, toy examples. This pays off in the large. Like, this is not terrible code, but let's try to rewrite it for practice. Yes?
And that bang is supposed to be equal sign, right?
If the host is not nilputter, no, that's supposed the or should be an end. That's what I screwed up. Both of those need to be true to have found the host name. Yes, thank you. Exactly when you thought your slides were okay.
Maybe a good motivation to use a monad here.
Sorry?
Good motivation to use a monad here to prevent this sort of mistake.
Exactly. So let's first adapt to uniformity, right? We have several different scenarios here of how we figured things out. We need everything to speak the same language of optional here. So the first pattern that we'll be adapting is the query getter pair. Very common. We're just going to write the adapter. Like there ain't nothing wrong with this. It's just we want a uniform interface, so we'll write one. Like we have our maybe hostname from args, takes the args, returns optional of string, does the thing. Yes?
I mean, there probably is something wrong with the two functions that you're probably doing a bunch of work twice.
Probably.
But we don't care.
But like that's like a standard C idiom. Like look at printf. I mean, yes?
Thank you.
Your use of functor here is in the sense of function object, right?
In this case, yes. But yes, I probably will only be using functor as function object because we're not doing diagram chasing, and I don't want to. It would be very confusing. So yeah.
Do you want to elaborate on why you're using a function object instead of a function?
Repeat.
Do you want to? Why are you using a lambda?
In this case, I didn't specifically have to, but it turns out overload sets get formed real quick and then you can't name them anymore. So I'm just hedging on the side of this is not an overload set, right? It's a first class thing that I can pass to things. So everything is going to be a function object unless otherwise stated because it's important, because we're going to get to overload sets. Okay, so this is a thing you might want to do with your code. Another pattern from nil pointer on nothing. This is a very standard, another very standard pattern, right? Return nil pointer if there's nothing there. We need to adapt this. We're going to write our own getenv with optional and coolness that does the thing. Notice how I didn't do the check for empty string here. I didn't do it because I would lie. Right? This is not the contract of this function. This function is true to the actual interface of std_getenv. It's just speaking optional. We're going to need filter for the other bit, right? So filter, what it does is the highlighted business logic, right? Like if the predicate is true, then return the value, otherwise return nil-opt. Kind of obvious what it does. The other two lines here are, we're going to need, some way to hook into filter to query the predicate, to remember the predicate, because we're going to be passing a predicated filter to other things, right? So we literally just need to return a lambda that captures the predicate. Yes, I should have done move on it. I said I'm not doing forwarding, because slides, right? And this is roughly what filter looks like. It's actually not. We'll fix it. So the first pass of putting it all together is, we're going to need not empty for the predicate, so we do that. So Fedor, this is exactly the pattern for like raising member functions to things, right? Which is what you did. But this is what we want, right? Like a lot of the time we're going to need to have the discipline to raise member functions to function objects. That's what we do. And so what we do then is we do the getenv, and then we filter on non-empty, which correctly short circuits, right? Non-empty expects to get a string or something that's a container that has empty. And notice I didn't constrain it properly. Again, slideware, right? So this is the and then compositional pattern. I don't have branches that are obvious. I can read this. The other bits of maybe hostname from args, it's the previous refactor that we did, right? And then we've got the pipe or else. I could have said dot or else. I just like how the pipe makes it obvious that we're going down. Dots are a lot less obvious. But all of these function objects that we have, like or else and all of these member functions, they're just lifts of the obvious thing. Okay, like don't worry about it. Unfortunately, we still need to lift this business logic in between. That's right now, yeah. And then we've got the value or, which is the defaulting bit on the end, which gets us back into string land from optional land. Okay, so value or is your escape from monadicness. The problem is we defined filter wrong, because filter always means or else, right? And so we're going to fix filter. It's going to be a little more code, but it's going to mean a little less code on the user side, which is what we want. So the business logic is still here. We didn't change that. It's just we now need to get the predicate from the closure explicitly as opposed to the lambda giving it to us. The reason we're doing it this way is because we have to put this in a header and we want linkage to properly work because it doesn't work properly for lambdas. So if you're doing this, you have to do the annoying thing. Like lambdas will not get you there. Things will be weird. We're gonna do our closure. Thank you, CTAD. We don't really need to do anything else. We're gonna make an operator parens, which was the outer lambda of the filter before, right? We query the predicate into the closure, we save that, we return that, it's all good. And then that is where we do the and then in the operator pipe, right? I'm lying here, closure actually has an operator parens as well that does the same thing. It doesn't fit on the slide. The reason you wanted to have an operator parens that does the same thing as operator pipe is because you want this to be a drillable thing. We'll get to drilling if I have enough time. But basically, if you have a monad of a monad, you want to do like or else transform something, and then that needs to like work. All right. Now we can omit the and then because filter is defined correctly. Notice how we have defined another monadic combinator. It's kind of nice. I can't do anything about the outer lambda because we needed to be lazy, and that's how we spell that in C++. As I said, we can't really have nice things. but this is nice enough. And now we look at this, right? And we're like, why the hell is the default host name there? And we'll get to that. But first, I want to show you a cute little implementation detail. We're defining this some optional concept. If it's like a CVRef thing of this template, we name it some that thing. And that allows us to do like some that thing auto-ref when we are taking them. That's really useful. And this is the fastest way we were able to do it. Notice that I'm asking some property of x. Then I say xref here. Why? Because adding an L-value reference is the fastest way the compiler knows how to collapse references. Because it's a built-in, right? And then the only two cases that remain for me are the constref and the mutable L-value ref, which is a two-way pattern match, which is way faster than remove CVREF-T. This compiles about a third of the time. It's very nice. And you're not stamping out any struct bodies. Why? Because these are variable templates, right? And therefore, they go into the global hash map, and that's it. There's no new namespaces. There's no new nothing. Prefer variables to : value. It sucks. All right. We want to fix the defaulting, because defaulting doesn't belong in a thing that says maybe get hostname from environment, right? Now we're actually naming things correctly. We give it the argc, we give it the argv, service hostname is in the documentation. We could have taken that as an argument, but this is in our outside the documentation, so it's not really configurable, right? And then now we're returning a stud optional of stud string, because why not enable composition, right? So this is just the code you already saw, except without the defaulting. And then once we're in main, like we can load our config file that is maybe there. And if it's not, we don't get anything. And then if we want the target hostname, we say, well, maybe get me the hostname from the environment that was supplied from the outside, or else get it from the config file, or else, value or default hostname. And now suddenly the defaulting is where we're doing the whole composition, right? We pushed the weirdest part of the problem up. And the weirdest part usually are hard-coded default values. So it's like, this is what you can do with optional. It's really nice, because things start composing. All right, so recap, function lifts on optional. We've got 4 of them. We've got end then, which takes a t to optional of view and gives you a function from optional of t to optional of view. We have transform, which is sort of like a bridge. When you already have an optional, but you have a function from t to u that doesn't know anything about optional, you use transform, and the flavor of transform is fundamentally different from the flavor of end then. Because end then, when you're using end then, you're saying this function can fail in some way. When you're using transform, you're saying this function can't fail. So when I see that in the code, I say, oh, I don't have to look here, this can't fail. It's kind of nice. But you need to know what things, like what flavor things have, right? And like we don't have that on CPP reference because we don't have how to think about monads there. We have just the function signature. We have the other monad, like the inverse monad, with or else, which takes the other thing that's nothing underneath, a function from nothing to optional of t, and lets us do defaulting. Again, notice how the inverse monad has a completely different flavor to it. The inverse monad has defaulting, the top level monad has short circuit on failure, right? And they're usually not used in the same like contexts. And then we've got value or, which is the escape. Like you give it a t, not even like a function, and it gives you a function from optional of t to t. It doesn't give you an optional, right? That's like how you get back. All right. Another monad that is really, really useful, except I hate it guts because it's wrong. It's expected. This is a monad for errors, but it's still not exceptions. Now, in the implementation bit, you might say, well, I mean, we know optional, right? Instead of nil opt, we get E, like our error type. But the flavor of error, like when you see error in your code, the flavor is completely different. Because if the patterns before were short-circuiting and defaulting, expected is about actual failure, right? Where you want to communicate something about that failure, and again, like short-circuit all the way to the end of the pipeline, fine. But it's like the morality of the situation is different. Like the severity of it. If you get an optional nothing, that just means there's nothing there. It's fine. There's probably, it's all fine. Like just try another thing. It's okay. With expected, like you probably should deal with this. Like that's what we're trying to communicate when we're using expected, right?
It's like the thing was expected.
Yes, yes, exactly. Thank you, Tony. This is the problem with expected, and also this is its greatest strength, by the way. So, problem, strength, two sides of the same coin. There are as many expecteds as there are E's. Because the bind operation, that is the and then operation on expected, can't change the error type. This is why this is not exceptions. So expected is a true indexed monad. It is indexed on E. Like you get the monad diagram per E, and those diagrams don't communicate at all. It like for the people who know the math. So the function lifts on expected are and then. This one should be pretty predictable, right? Like it takes a function that takes a t and returns an expected of some other type u and the same e. And it gives you a function from expected te to expected ue, right? Transform, again, is the bridge that doesn't know anything about, like for functions that don't know anything about expected and therefore cannot fail. Very important in this situation even more. From t to u, you get a function from expected te to expected ue, right? Or else, now we're inverting the monad again. We're operating on the error part. You get the error, an expected of t error, but notice that this one also can't change the error type.
Okay, why not? Because it seems like it ought to be.
Because if you are short-circuiting on the expected side, because it's just the reverse monad, right? Then you don't actually run the function. You keep what you have.
Ah, okay.
Right? So you can't change anything.
It's not that you couldn't write a lift that did that, but it wouldn't.
You're skipping ahead.
Okay.
Okay? All right. You need a completely different category to do that. It took me an hour to understand my own theory with Lisa on a blackboard. All right. Transform error is an explicit bridge between diagrams, between these indexed monads. So if it is like transform but for errors, you might think that from the name. It gets a function from e to e prime, and it goes from expected te to expected of t e prime. It leaves t alone. So if there's already a t in there, you're gonna get the same t, but like with the error changed around, or you're actually gonna run the function, get another e if you have an error. Value or, again, the escape. Okay.
You can't escape to an e?
No, because if you have a value, you get the value.
Yeah.
And like if you manually computed that t is another expected, then you have escaped into the other side of the looking glass.
Yeah. The thing to E would be like, I had a value, but I really wanted an E.
Yes.
It's like,
yeah.
probably
You could do that. Like it's
not
just
as useful.
It's not as commonly done. Let's call it that, right? So expected is a domain-based composition type. It's not better exceptions. The patterns again are like we have short circuit, like we did with optional, and then lifts functions that can fail. As I said, transform is the bridge, and the sad part of the monad, right? Like we've got the happy path of the monad and the sad part of the monad for expected. We don't have this for optional. There's no sad path in optional. There's just the inverse path. There's the defaulting path, right? Or else is recover, right? Like you can try to recover and then you can go back to the value channel, like the happy path, or you fail to recover and you get another error or keep it or whatever, right? But that's what or else's flavor is in expected. It's recover. And transform error is literally like, I need to go to a different domain. You very rarely see that because of the nature of the composition here. Yes?
I feel like there's something missing, like value or that takes the error, and like based on the error you can determine a different value or something.
or else.
I think that's or else.
Ah, right.
That's exactly recover. It takes the error
Right.
and
Right. Yeah. Okay.
Yeah.
I guess because you always assume recovery.
yeah, like it's all symmetric, right? And because it's all symmetric, it's like it's all symmetric. Like we can just no, we have conventions, right? You're either on the happy monad, so use the happy monad combinators, or you're on the sad monad and you're using the sad monad combinators. Yeah.
So just from my understanding, or else in both cases here is extend in the comonad type class and value or is extract. Is that what we're saying? I think
That's too much theory for me. I don't know.
no, it's just what Haskell calls these things.
Oh, I don't know what Haskell calls these things. Yes.
I wouldn't put transform error on the sad monad because you can also use it on the happy monad. Then you simply pass E success to E prime success. And
Sure, but
you should have called it natural transform error because it's a natural transformation.
There's no E success.
there's no E success, right? Like what it is
Yeah, okay.
like here's the thing. If you look at this diagram, it's completely symmetric both ways. Transform error is bind on the sad monad, or else is bind on the sad monad. Transform error is transform on the sad monad. Right? Like it literally, it's just the flavor that we're talking about. You have all the power you need in all of these combinators. There's nothing missing. It's just how do we treat them? Yeah.
The or else you get an error and you try to recover it. Could this second E be a E prime of some other type of error?
No. That's
Not in
the
keep short circuit.
not you can't short circuit in that case, right? We will like that is why I don't like expected, and that is why I did this whole talk in like this whole library. Like this isn't the standard library, right? Like I'm teaching you how to think about these things so that when I extend it and hopefully give you something way more powerful that actually is exceptions, but better because you can meta program on them and do generic matching. Like that you know where we came from, right? Yes, this is a pain point with expected. We're solving it. Thank you for noticing it, right? That means this is working. All right. Parsers are a good fit for expected. Now, Zach has written an actually nice to use parser library. He's not using expected, he's using maybe. For reasons, that's because he's hiding the errors in like a context. He made up his own monad. That's fine. Like you can do domain specific monads and you should. Like in our prod thing, we literally had a high Redis monad. Okay, that was awesome. I loved it. It had its own, IO context that it was running on, and like the whole thing, and everything ran correctly. We loved it. make your own monads. Like, I'm trying to teach you how to think with compositional context on the examples that we already have. This is not like, this is not a talk about these things, right? This is a talk about how to think about these things. Okay, so we've got parsers. We are gonna say our domain-specific error type is parse error. It's gonna carry some information about where the error occurred. Turns out that a pointer is not exactly good enough because you often want to retry parses, which is the recover part, right? So we're going to give you the rest instead. And effectively, every subgrammar signature is going to be, give me a span of char const. What I'm parsing is contained in the subgrammar. I'm returning a stud expected of a pair of some grammar node that I parsed and the rest. Or I'm returning a parse error. This is perfectly fine. And because that's a mouthful, we're going to make this use a parser for type alias that gives you the stud expected of the thing that I am parsing and the rest. Like, it's literally the thing that you just saw. It's a parser for int, right, in this case. All right, this is dense. It's supposed to make you feel scared because this is procedural code, right? It's not completely correct even. Like, I'm not checking for overflow. This is not a production grade parser. This is just to scare you. Literally, like, I look at this code and like I can reason through it. It's not that bad, right? But because it's short. But the because it's short is doing a lot of work here. So I'm going to try to show you again how you can refactor this code into more lines of code that are easier to prove. Sorry, Hannah?
There's a bug.
There probably is a bug. All right. Procedural code has bugs. Okay. All right.
Can I quote you that?
Yes.
Why procedural code has bugs?
I mean, I tried. This is the third time I'm giving this talk. I mean, I reworked this substantially between each giving, and this room is special, so it's an extra heavy kind, but still. So we're going to do parse digit, right? Parse digit should be easy. We get a span. We're returning a parser for int.
That's a bug.
Yeah. Same.
Sorry?
Same bug.
It's the same. What's the bug?
Just the 9 should be on, like, should be greater than or flip your 9
Oh,
less than.
yeah,
Source
yes.
should be less
You
than
copy
9.
pasted it.
Yeah, I copy pasted it. Sorry, this is what happens when you make slides at 3 in the morning.
So functional code also has bugs?
No, this is the procedural part of the functional code. But the thing is, a test would have caught this, right? Like, it is, like, I trust my CRCs in regular code. Like, I wrote this code for the slides. Because, like, this is not how I'd actually write a parser, right? Like, this is to show you how you can combine things. So that's, like, how you sort of parse a digit. You want to also parse a positive digit. It's like the obvious stuff, except for the fact that we're doing parse digit to start the parse of the positive digit. And then, if we actually manage to parse a digit, notice how this lets me get rid of the range checks, because I did them in parse digit already, right? And then I effectively just filter on is first more greater than 0. So if it is, I'm returning it. Otherwise, I'm returning an unexpected of the parse error of the source. We can rework the integral portion, which is parsed unprefixed integer. Like, it has no minus or plus. Parser for int. I apparently forgot to copy pasta this one. We parse a positive digit, and then this can't fail because it's perfectly okay to not have more than one digit. We do a while loop and just parse digits and aggregate them. That's fine. Like, we have procedural programming. Like, in the really small, that's probably fine, right? like we don't have to go all the way functional. Like that's craziness. And then we just return our stood pair of result and the rest, and we're good. The sign portion, we need to do our range checks. You know, we see if it's negative, if it is negative, or sources. I probably screwed this one up too. If it's not negative, yeah, debugging on talks is the best kind of debugging. You see what this is doing. Like the fun part here is the parse digit source, transform, return pair 1 in source, and right. So yeah, did I probably screwed some more of this also. And once we put it together, then it's like maybe parse sign, right? And then you get the sign, parse done prefixed int, transform. Oh yeah, no, that was fine. Sign first, P second. You're fine, right? All right, ish. Like this might be better, might not be better. I don't know. Yes.
Is something coming that gets rid of the lambda within the lambda? Like this goes to the right?
No, because this is you're in a maybe context here, right? Like this only happens if you're on the truthy part of the expected. So you can't get rid of the lambda within the lambda. It's kind of integral, but you can write more named things that you can then combine, and then you get rid of lambdas. Like we'll see that if like. All right, so this is very limited, right? As a compositional context, you only get one error type. You still get bugs in the procedural parts, especially if you don't have tests. And the real problem is that stud expected is not exceptions, right? Like we can't also return IO error if we weren't operating on a span, right? Yeah.
Can't you return an error type that's a variant that contains both?
Stop skipping ahead. All right, yeah, like you can, but variant doesn't work. Variant is bad. Variant is not a compositional primitive for C++ because we have overload sets. And that's all I'm gonna say right now about it. Okay, so towards multiple errors, like we're gonna need this concept, any of, it's the obvious thing. Like it's any one of these types, modulo CVRF qualifiers. So C++ has exceptions. We want to catch any of them. And I screwed up the line numbers. So basically, G throws something. I don't know what. I want to catch any of these 3 exceptions, but C++ doesn't let me do that unless they all inherit from the same base. And then I can't subselect from things that inherit from that base. It's really annoying. So did I get all the exceptions that this function can throw? Who knows? Like the compiler doesn't offer me any help here. I need to actually go read the docs and pray nobody changed it from under me. So how about this, right? Like if we instead return expected of int variant of all of these 3 error types, just like Jeff suggested, we can use transform error, and then we can stud visit. We have any of. And that gives me an expected of int e2. And that's sort of fine. And it fails to compile if I have an error type that I can't handle, right? So that's better. The problem is if I want to do something like this, right? I have transform error. I get the error if it happened. I'm stud visiting with an overload. You all know what this does, right? If it's E1 or E2, I return E1. Otherwise, if it's E3, which I didn't need any of for, but you know, we return E2. And stud visit refuses to cooperate. You need to do your own type things, and you need to annotate every one of your lambdas with the final return type, and that is just awful for any kind of genericity. It does not work as a compositional primitive. So we're going to introduce something that does. We're going to call it sum of t's, and we're going to sort and unique the t's. This is very important because category theory. But basically, we're going to define transform on this weird type, right? And this transform is going to say, well, you are going to give me an overload set. Sorry, I don't have good notation for this, so I had to make some up. Bear with me. You give me an overload set, which is these two braces, of functions from ti to sum of uij, any sum of any types at all, including nothing, although you can't really return sum of nothing because it's the initial object, so that doesn't work. But you could type annotate that if it could never actually happen. You can also return something that's not a sum. Like you can just return a type, we'll just union all of that together. And then we're going to give you a function that is actually a function from the sum you actually want the function from to a sum of all of the return types unioned together, sorted and uniqued. Okay? Because this is how overload sets work. Now this is a fun kind of transformation. It's not exactly straightforward to code. Sum is a type that you cannot do in portable C++ because we can't sort types at compile time. And it actually is very important that there is a canonical order of t's because you must not be able to form two sums of the same set of types in a different order. Otherwise, the theory doesn't work. So that's why I have the type ordering paper. Like, we need this, because otherwise we can't meta program with other overload sets in any kind of sane way. But this is what transform does. It's like std_visit, but you don't have to annotate the return types. We just compute the sum of all of them and sort and unique them. And now you understand what it does. Like, it's not any more magic than that. Because we union these things, and if you just return like error2, we just treat that as a sum of error2. Sums cannot contain sums. This is different than variant. Variants nest, sums don't. They auto-flatten. You might be surprised that there's a coherent theory for this. There is. Trust me. I was skeptical at first too, which is why I did all the theory. I wanted to make sure that this is actually sound. So then Bartosz Milewski helped and we got somewhere. All right, so that's what this is doing. Notice we are effectively redefining what the hell invoke means. Right? But I hope that you're all comfortable with this transformation. You get a sum, you can invoke an overload set with whatever is in there, you get a sum on the output. There's another operation that we need to define. It's like a join, which is what I said, like sums can't contain other sums. If you want to join two sums, you get the sorted unique union of the types. If you try to join a type that's not a sum and a sum, you get a sum with that type in the type list, sorted and unique. Like we always sort and unique. There's a nice little, yes?
Your bottom two lines then should be
The same.
the same.
On the right.
Where you put the T, just to be like,
Yes,
you
they
sorted it.
should be the same. Like,
Okay.
yes, it's all modulo sort and unique.
Okay.
There's a nice little type alias in the library called sum4, which you give it any type list and it'll do this for you. Which is why you don't have to guess what it is, because we have a static assert in the sum class that you can't make it if it's not in canonical order. All right, so this is what this looks like, right? As an example, we've got a sum4 int and string. We initialize it with an int2. We transform it with an overload that takes an int that transforms, into a negative int and a positive int. Notice I'm using sum4 because I don't know what the canonical order of those two is. I don't have to. The library does it for me. And then if it's less than 0, then I return negative int x. Otherwise, I return positive int x. And I should have called that non-negative int x. But fine. And we just have fn identity for the string case. We'll just return the string. This is very useful if you want to ignore things. And what we get out is the obvious thing. We get a sum for string, negative int, positive int.
Sorry?
Yeah. Yes, it's this one. Yes.
Does the ternary operator actually work?
Yes.
Because
there's common type defined for these.
Yeah, but it's a distinct type from the two alternatives, right? Ternary doesn't look at common type.
That's a good. Okay, fine. Pretend there's an if.
Yeah, we have a macro for that exact purpose. But...
Okay, fine. The common type. Yeah. The common type is defined, but would be nice if the language let us do this. Yeah. You need an if then else. Yes, thank you. Slide code. Yeah. Sorry.
Yeah.
Yeah. Now, the reason we defined the join operation is because now that we have the ground truth of how invoke works, we can say, well, this distributes over monads. So monad functors are going to obey this invoke property. So we have to define join for optional. Optional of t, join optional of u. Notice t and u might be sums, right? Are optional of join tu. So join distributes into the monad. And if neither t nor u is a thing that has join defined for it, then you don't work. You fail to compile. That you're doing something stupid. It's outside of the theory. Now, this is not an actual operation in C++. Join is implicitly coded all over the place because we have to. It's annoying, but we need to define it for your brains, right? So the way this works is all the monadic operations need to obey this property. So if we have an optional sum of string, and what was that supposed to be?
I don't know.
No, actually, that's just a stray comma.
Oh, okay.
Yeah, that's just a stray comma. Or else needs to obey this property, because if we have nothing, which we do, then we return optional of int. We do the join between sum of string and int, and that's why we get an optional of sum for int string, right? If we didn't have a sum inside the optional, join doesn't work because we don't want to lose the type safety. If you didn't put a sum somewhere, we're not going to just boot you into that world so that you can still have the normal monads that you're used to, right? But if you have a sum somewhere, we're just going to say, okay, you're doing the thing, right? What about expected? Well, same thing. We need to define the join. Join works on both sides of the monad now. You already know what it does, right? Let's say we've got parse line of string. It gives us an expected of result and parse error. And if we have read line of file, it gives us expected of string IO error. We need to transform the IO error into a sum so that we get this property. So we've got this nice little functor called sum error, which is literally lift the thing, right? And then you do the and then parse line, which notice fails with parse error, and you get expected of result sum IO error parse error. So the lift into the weird and magical world is explicit the first time, and then you just get it. Anyone want this slide up for slightly longer? No? All right, perfect. All other monads follow the same pattern, right? All of the functors obey this. Back to exceptions. This means that this just works, right? Like we have our own G2, it returns expected of int sum E1, E2, E3 instead of the variant that we returned before. G2, pipe transform error, overload, any of E1, E3, return E1, otherwise E2, print X, return X. Like that's just a, we're doing something different than identity. I don't care. It's error handling, who cares? But you get the right thing out, right? You get an expected of int sum E1, E2, because we erased E3. E3 is no longer there. If you don't handle all the exceptions, you fail to compile. That's what we wanted to do. We wanted to have the compiler prove our code. Like you add another way to fail, you're going to fail to compile until you fix all your code. That makes it really easy to do refactorings, I gotta tell you. You don't even need to run tests. It will just point you at the code that's wrong. Like it really saved us a lot of time, like just developing this thing. And like the second we had another weird thing that some exchange did, we like, okay, this goes here, we've got another state. It just failed to compile for like 3 days until we fixed everything, and then it was correct. Like honestly, really great experience if you discount having to read compiler errors. But I like reading compiler errors better than I like reading stack traces and tests. You want to let some errors through? Do it explicitly. Just put identity there. That's how it works. Just put identity there. And yes, internally we had an identity with a type constraint, so you could just list the types that you want to let through, and the rest, still failed to compile. So we've got another part of this, which is called packs. Because notice that so far we've only been doing functions of one argument. I don't know if you've noticed, but C++ has functions of multiple arguments. Kind of matters. So we need packs that also have a transform, right? Just like sums. So sums are a weird coproduct. Packs are the product that's as weird as sums are. Okay, so packs can't contain other packs. They auto-flatten, just like Perl lists. You want structure, use a tuple, right? Or use the identity monad. Like you can have that with a pack in it. We're not going to look through that. That would be cheating, right? But, have a pack. When you try to invoke a function, the pack will unpack into arguments. So that's how that works. We've got a pack of 1 and a string. We transform it. You get an int and a string. And then you can return a pack also. And then the next transform is going to call the pack with 3 arguments. And then we can cout it and whatever, right? It's fine. They also have their own join operation. Cat, right? We use an ampersand to represent it. Where if you've got 2 packs and you're concatenating them, you get 1 pack. We flatten. We don't unique and sort. That's not what arguments do, right? But because this is for calling things. We do the same thing as for sums, though. If you try to concatenate a pack and a type, you get a pack and the type. Right? Like, so we will auto lift it for you because that's nice. It turns out that it's very nice to be able to write functions that don't return packs of one thing just because you need to concatenate all of those in the transform, right? Same for the other direction. And if you have a pack of packs, that's just the pack. So that's the flattening bit, right? Okay. It still distributes inside monads. That's the important bit. So if you have multiple monadic arguments, why is this cut off? I guess I'm presenting on a different resolution. So let's say we've got a config object, right? It has get maybe, like you give it a key, it gives you something back, like an optional the thing that you want. It also needs to be the right type because you give it the type. So when you call get maybe of string, you're expecting to get a string back. And we want to parse a socket address out of the configuration. And we have like a connect function that takes the configuration. You shouldn't take configuration and connect, but this is an example. And it returns an optional of the socket address. Yeah, I'm gonna really need to figure out what to do with this. Let me see if I can make it smaller. Ah, yes, good. Sorry about this. I went through all the slides, but this one I guess just overflowed. Is this possible to read from the back?
Yeah.
All right, so we've got the config, we've got the socket address, it's an aggregate. We have connect, and here's our pack, right? We have get maybe stud string, a host name, get maybe int port with an ampersand in between. And the type of this little construction is one optional of pack of stud string comma int. Because if you short circuit, you have short circuited. That's why the ampersand isn't lying. And then you can call transform. And you get 2 arguments, because that's what pack does. And then you can create your socket address and return. But this turns out to be a really, really important pattern. What would we do? What do? We name common patterns. So we have this function. I can now reset the thing. We have a function that's a constructor lift. It's called make of type. And you can just call transform make socket address, and that's what you do. So this came out of the desire to not have Tony's camera, right? So we said we don't want objects that don't yet make sense, right? And because we have some, we can afford to have multiple like representations of the same moral object in different states, right? So if you're initializing in steps, then you have step 1 object type, step 2 object type, which is bigger, step 3 object type, which is even bigger. And you do this in steps. And you don't call the make function until you have everything and everything succeeded. This made parsing configuration a breeze. This made parsing stuff we got off the wire a breeze. Because you literally couldn't make, a trade object without everything being there. This is basically the rule that we had, which is make implausible program state unrepresentable. So we did a lot of strong types that asserted their invariance in their constructors, and then we didn't have mutation. Like you made a new object and you overrode the old one. With move semantics, that actually happens to be not too bad. Error packs, now you already know how they work. So let's go through this. We get some JSON. We want to return an expected of response or a parser, right? And we, get the version. And then if we didn't get the version at all, then we return a nice user visible error. Otherwise, we parse the version. And then we say, well, it better be the version that we know what to do with. And otherwise, we make a parser. And we get an expected of version parser. Super easy. We pack that with maybe ID, or else return a parser, like I need an ID. We parse the int. We make the ID. Right? Like this is how this all works. Like you parse the native type, you do all the filters to make sure that everything works. and then you make the strong type that you've just checked the preconditions of. And that says, I have checked the preconditions. You don't get to make it before you check the preconditions. This is how we avoid exceptions, right? Like, you can't make it until you're right. And now we've got a pack of all of the things that we wanted to parse out of the JSON, and then you make the response type that is like the overall thing that you were trying to parse out of a JSON message or whatever. Yes?
Does your concatenation order have to match the order of its field within the structure?
Yes, because it's a pack. Like, make is just a lift of the constructor. The pack just calls a function, right? Like, there's nothing overly magic about make. It's just a function that calls the constructor.
It's in the order of the params to the constructor.
Exactly. But it short circuits, right? Because if you get an error, like, you're gonna get an error. You already know that. Yeah, you're never gonna call make if any of these fails. Yeah, so we didn't forget error checking. There's no way to make a response if we fail anything. And we validate everything due to strong types. So strong types, use them. Like, version is just an integer, but it's a struct that has an integer in it. The constructor validates to prove that we got the thing, but like, if that's an assert. Like, we don't do maybe on constructors, we do maybe before the constructor, right? The response takes a version, not like an int. Only plausible business logic should compile. Again, encode things in types until that is true. Obviously, there's a limit. Like, use your judgment. But where you set the bar for your team is the difference of how long you're going to spend staring at compile time errors and runtime errors. Sometimes you need to make the trade-off a different way. Like, use your brain. All right. Things about strong types. Price is a point space over the integral module of price delta. If you don't know what that means, it doesn't matter. Stud chrono does it. Look at what it does. You'll figure it out. Things like that, right? And so where we got to now is almost to the point where we wanted to get. So we know what sum does and what it does to monads. We know what pack does and what it does to monads. And we want to put them together. So sum is sorry. I need to motivate this slide. This is right. All right. So sum calls one function that corresponds to the type that's actually at runtime in the sum, right? The transform on sum does that. But it computes the return type for all of them, right? So that's what transform on sum does. What pack does is it unpacks into arguments. So we have two kind of orthogonal things that we're doing. And of course, a pack of sums therefore does multiple dispatch. Because of course it does. It has to. There's no other way to define it. Because we flatten everything. Like, you can never call a function with a sum or a pack, because that's the whole point. Like, they don't appear once transform's done with them. They're one layer. And so that means that if you have a pack of sum AB and sum XY that you instantiate with A and X, because of course I've got a bug on the slide, then you're going to get the correct overload. That means that pack and sum also have a distribution law between them, where a pack of two sums is the same as a sum of four packs, right? Like those four packs. And of course, transform has to find the common type, because that's what transform does on sum. Like, so that's the algebra, right? A sum of t, 1t, notice there's no pack, is the same as a pack of t as far as transform is concerned, which is the same as a sum of pack of t, which is the same as a pack of sum of t. We say these are the same things. Like, I'd actually love to completely make them one thing, but it's hard to do in C++. Like, I want only one of these to be representable. Like, and if you type one, you just magically collapse into the correct one. I want to do that. We're not quite there yet with the library, but that's morally what we want to do. For multiple t's, of course, as I said, pack of sum of ab, sum of xy is the same as a sum of pack ax, ay, bx, and by. And notice how the second construction, even though it's longer, it flattens out the index space. So you're actually paying less for memory because you've got one index and more types, which means that you can directly index with that index into your function table that you do for multiple dispatch, right? You've already done the dot product effectively. Of course, it works for more than one. Like, there's nothing saying that we only need to stay with two, but the examples get a little long. We also do the flattening, as I said. This is kind of a recap. Sum of sum is the same as sum, because it has to be. Pack of pack is the, like they auto-flatten. Like pack of tu, comma, v flattens into a pack of tuv. Because otherwise it's hard to make transform do the right thing. So we just make it do the right thing. But it turns out that this is exactly how overload sets work in C++. So I would like you to think of an overload set as a function defined in parts, where the part you get is selected with the type list that you've got, right? That's kind of the mental model that we have. It's not exactly how finding all of the overloads works, but it is how selecting the overload works. And so that's why we like closed overload sets when we're doing this, like overload, where you give it a bunch of lambdas. That's still an overload set. It's just closed, right? Like, you can also lift whole names, which are open overload sets, but still they work, right? So the normal overload sets don't compose. Like, if you return, once you have picked your function, then that function can only return one type. And if that type isn't sum of packs, and the next thing is transform, C++ will not give you any help with composing it with the next overload set. Like, you will hit one function and one function only, and that function is gonna have one argument. If you make f of g of h and so on, right? C++ doesn't give us support for this, so we need to build it ourselves, and that's super annoying. So that's why we effectively had to completely redefine what invoking a function means. So now pipelines work with this, right? Like, if we have the sum pack thing. We did state machines exactly like this, except for the fact that instead of just a sum coming out, a sum and an effect came out. So the effect went into the IO thing and the sum went into the next state. But this is actually really nice to read, right? We've got some states, they're the ones. We've got some messages. That's generally how state machines work. We have a concept that says, well, this is some live state. We consider initialized, connecting, and connected to be live states and everything else to be a dead state. So once we want to define our transition function, we get a state, we get a message, we expect those to be moved into the function, right? And then we make a pack of these, and then we use transform, because of course we do. And then we give it our overload set. So if you're initialized and the message is connect, then you either go to connecting or you fail. If you're connected and that auto is wrong over there, that's a bug on the slide, and you get a data packet, then your next state is still going to be connected or fail if the message was a failure. But you probably want to do some effect which comes out in the production environment but doesn't fit on slides. The other two are a little more interesting, right? Like if you have some live state S and you get a stop message, then you just go to disconnected. That's what you do. And if you have some live state and an unexpected disconnect, then you need to go back to connecting or you fail. Notice that I didn't even implement these and you already know how this state machine works. Right? And then if I get anything else that's an invalid part of the matrix, I go to fail. What else do you want? Like, you can meta program with states now. It's super easy. Like, you want some, context to be injected in the front, just put it in the pack. It'll be on your call thing. It's great. So this is what a graded monad is. Like, they're relaxed. Right? Like, version of error is like you open a path and you get an expected file or of like does not exist, or you get a permission error. Sorry, it's cut off. And then you read a line and you might get an IO error, and then that's your expected of string of sum of all of the things that could have happened before plus this one. And then you parse a version and you also can get a syntax error. That's fine. It just works. That's how exceptions work. Except now it's all in the type system and you can meta program against it and you can make it not compile. So expected T sum of pack of whatever is a closed polymorphic equivalent to C++ exceptions, except better. Except worse, because again, you lose type erasure, right? Like for some people, that's actually important because they want stable ABIs, which is what exceptions give you. I hate it so much. I hate it so much, but I do concede that sometimes that's exactly what you need. It's a tool, it does one thing and one thing only, and we make it do way too many things. We should do this a lot more often, but we didn't have the tools. That's why we're writing this library, right? So this is, another example of how we can handle errors generically, just to remind you what we should be doing. Back to get maybe. We can drop the type arguments and get maybe now. Because remember, we had to give it what we wanted before. Now we can just return a sum. It's fine. We'll just compose. So this get maybe is no longer a template. It just returns a sum of all of the things that it could. And now connect, we can kind of rewrite it. We get the host name, we get maybe the port. And then, like, if it's the right types, then we make the right thing. Otherwise, we just say it'll fail. Right? No more annotating this bullshit. You can just pattern match it out. You're fine. Drilling. What if I have a monad in a monad? So what if I have like an expected of an optional of int? And I initialize it with an optional of 3, right? Then I can transform, but that outer transform is on the expected. So that means the function that I'm mapping the value of the expected, which is a monad, which happens to be optional, is also transformed. Like I need to lift it. That's what transform does. So then I lift that. I have a lambda that just, formats the int, whatever, right? And out I get expected of optional of string. And suddenly having nested monads is no longer annoying. You can actually represent things the way you want to. Notice that packs also compose. So packs will, because the join operation sees through, right? So if you have a pack of like nested monads, you're going to get a pack on the top. Nice, huh? So congratulations on surviving this gentle introduction to the SumPack caboodle. This is what makes overload sets composable since last year. So this has been my research. And Bronex, we actually wrote production code that shipped and worked. And the only real errors it had to do with the shared pointer, which, well, we had to use it because ASIO doesn't require the use of shared pointer, but just like objects, it's made of Velcro and it attracts shared pointer like nobody's business. Like this, like, like really, it's very difficult to use ASIO without shared pointer, and that was the only real issue that happened in production we had with the system. It worked beautifully. So yeah, that's it. That's my talk. Thank you. Yeah, Zach.
So you are sorting and uniquing sums.
Yeah.
Elements of sums. Do you need to do the sorting for the uniquing, or is the sorting important on its own?
The sorting is important on its own. You could have a multi-sum, but you'd still need to sort it. That said, you couldn't really, without some weird differences to transform that I would be very glad to explain to you over a blackboard, because it has to do with commutative diagrams, and that's not for this room. Yes?
So you mentioned that this is not portable between compilers because you can't represent types as values.
Oh yeah, so we do sorting. We do sorting with pretty function, which is a horrible misuse of pretty function, but it's the only way we were able to do it. So we do actually do some normalization to have same order between Clang and GCC, because we actually normalize the thing you get out of pretty function because we saw what the compilers do, and then, you know, normalize the text at const x per time. But still, like, if you're lifting, you need to be kind of careful to only really use lambdas and combinators in implementation files, because if you use them in headers, you get things that don't have very well-defined linkage, and then they don't correctly link between translation units. And that has nothing to do with compilers. That has to do with the fact that our mangling is shit. Yes, Tony?
Two things.
So, you're next, Steve.
Okay. If I have a type, like it's an ID type, something really simple, and its only internal constraint is the IDs are greater than 100.
Mm-hmm.
The first 100 were something special, so they're greater than 100. I can put that in my constructor. You passed me 95, and I have to throw, saying I can't do that.
Mm-hmm.
So you don't want that because you don't want to throw. You have to put that constraint outside my type, and therefore, where do you put it? You can put it in a statement out, inside this mess of code.
Yeah.
Or you can put it in a factory function.
Yes.
And is that which?
So we again, this is like, you need to develop a convention within your code base where to put it, because again, the language doesn't make you do anything specific. What we did was, if we had these kinds of constraints, we made a static member function called make that returned a monad,
right,
and made all the constructors private.
Right, got it. That's okay.
Yeah.
I expected something like that. Okay.
Yeah, that is what we did.
I expected something like that.
Mm-hmm.
Yeah. Checked exceptions have been tried in multiple languages, and everyone always goes away from them.
Yes, because they don't have support from the language that auto computes that set.
Well, and it's also because of like pointers to functions for C++. It's things like pointers to functions. Like, how do I know? Because we don't have the exception list in the pointer to function type. You quickly lose track of, I don't know what this is going to throw.
Yes.
Okay.
So,
but this doesn't have that.
Yeah, because we're basically saying the set of exceptions that you're throwing matters to the catcher.
Yeah.
It doesn't matter to the interface. It's a result of the implementation strategy, but it matters to the catcher. And so it's incidental to the interface. Okay. And so you should compute it, but we don't get support from the language to do that, so we have to do it ourselves. And I think that's the difference between checked exceptions don't work and checked exceptions actually do the right thing and are helpful to use.
Right. The thing was they were just annoying to have to type. I had to type out.
Yeah, but here you just say ID,
Right.
right? And so like that's why like the generic thing gives you all the rope you need. All right, Steve and then Kirk, so you don't have to hold your hand up. Sorry.
Okay. Two, and I hope they're both really quick. If I understood correctly, you don't care about the particular order you're using for types. You're just asserting an order exists, and that's how you're sorting them.
Exactly. We need a canonical representation. We need a canonical name for some.
For that collection,
yes.
that set.
And I keep walking around this, so I'll just say it. The reason you need a canonical name is because if you have two names, then you can form two functions from morally the same thing that aren't the same function and put them into the same overload set. Therefore, you no longer have the property that there's a unique function that gives you the embedding that transform has to do uniquely, right? And so you actually invalidate the correctness of the definition of transform and join if we let you make two differently named sums that mean the same thing, right? And so that's really the theoretical reason why we absolutely need a way to collapse these types.
Yeah. Okay, and the other one's sort of related, but just in terms of the notation that you're using. So when you constructed a pack or a sum and had like a left T and TS's or a TS's and then a right T.
Yeah.
And those are equivalent. They really get sorted into the list of, okay,
correct.
Yep.
But the reason I wrote it that way is because the join for packs is has the same diagram.
And that property is important.
Yeah.
Right.
Not for packs, just for sums.
Yes, some sort of unique packs are argument packs. Like they need the order.
Sure.
Yeah,
for the argument packs, they're not. But a collection of those with one on the end was the same as just adding it.
Packs concatenate and auto flatten. Sums concatenate, auto flatten, sort, and unique. And expand. And packs expand sums into sums of packs. They do the cross product. They do the Cartesian product.
Yeah, I just wanted to say that when you're creating function pointers, you're type erasing. And so if you're type erasing, you don't just type erase the values that are going in the arguments, you also type erase the error that you're producing. So either your functions that you assign to that pointer have to have produced a type erase error that matches the function signature, or it should fail to compile.
Yeah. There's another thing I kind of want to mention. I'll next. This SumPack caboodle comes up in the implementation part of P2300 and every other asynchronous library ever. Kirk's RxCpp calls it a notification, right? Like, I didn't make a brand new thing here. I just extended it to the point of closure where it was consistent with itself and the compositional nature of things. And I'm saying, I think this is the theory. I think this is the complete theory. And so because I think this is a complete theory, let's try and make it work and not have me hack the language this way, right? I don't like that I have to do this, but I think this is what calling overload sets actually means in C++, and we should have support for it. So Jeff was next, and then, yeah.
So when you get reflection, does that solve the portability problem?
No, actually. I need to get the const per type sorting, which is P2830, which is effectively going to need to fix a whole lot of bugs in the Itanium ABI to get it right. And we're doing that. And it's going to be super annoying. And it's going to be a lot of my copious free time throughout the next, several months. But fortunately, there's a bunch of compiler people also helping with it, like Ian Sendo and David van de Voorde are there. Like, the fundamental problem is that our linkage model is shit, right? And we, the Itanium ABI only distinguishes things that it absolutely has, and its bar for what is okay enough is it's different, but we actually need it sorts consistently, which is a stronger property, right? And so it's very complicated. But we're trying to get our brains around it. Like there's all kinds of weird things, like you can have mutually recursively named entities in C++. Like you don't even want to go there. Like it's horrific. And so like I have examples where the Itanium ABI produces names that are differently ordered based on instantiation order. Like it takes 5 lines of code once you know what you're doing, right? It's a really big problem, but once we solve that, we're also going to have, hopefully a slightly better idea of what it means to have a decent linkage model for this. But that's kind of like an implementation detail, right? Like I am saying you already know what this does. It sorts in uniques. There's some order that's given by God, right? Like, and now I have to somehow make that happen because, of course, I don't know about your beliefs, but I don't believe in one. So, yeah, okay, you.
Yeah, you said earlier there were certain things you didn't want to mention in header files, but only in
lambdas and anonymous types. Like they don't have well-defined linkage, and because you mentioned it in a static context per variable that you are then using in expressions, those things end up in names of exported entities very easily, right? And so that's kind of the problem. Like, so here's the thing, like this goes further, right? Like there's combinators where you get you have a monad that has a function in it. And then you want to maybe apply that function that's in the other maybe monad, right? And so that functor that's in the maybe or not ends up, of course it ends up in ABI, right? So it's lovely. Like basically you're compiling everything from source all the time. And that's why I said the compile times are kind of horrific, but on the other hand, theorem provers are also slow, and that's what we're doing. So I'm not too bummed out about it, but
So you mentioned restricts. How do you actually handle?
Right, not restricts, but like requires, you mean?
Yeah.
Yeah, so how do you handle these overload sets and stuff? Kind of ad hoc, right?
Well,
like
you said that you specifically didn't want to require because the failure is undecipherable.
So requires is a thing that in this context you use very sparingly.
So what do you use instead?
So you use static asserts.
Oh, okay. So you don't restrict the template. You just let it go in and static assert.
Yeah, because you aren't doing like, okay, so like this is like not a general thing, right? Like when you're making overload sets in this kind of context, either you have things that are already customization point functions and like have their own requires specifications and all of those things like on the overloads, or you're making your own overload sets. At which point you actually have a closed type list that you're pattern matching against. And therefore the requires clauses should be just enough to get the right, like to get into the right overload and no more. And then you static assert that you actually got everything inside there because you want the error. You don't want the sphinx.
You don't want that to not exist suddenly.
Yeah, Kirk.
So I've been encountering this in an implementation of T2300, and I found that static asserts happen too late, especially in the context of the chains of expression support. And so what I've started doing is I've started creating assert traits.
Very nice. All right.
I put them in my required clause, and they static assert if they're false. And so I have a set of spin A traits that are non-assert, and then I have a set of constraints traits that are asserting.
That's a very useful thing. Yes, I will steal this.
Please do.
Thanks.
Andre. Yeah.
Yeah, I'm very sorry, but I've got to pick on the name. Because we have in the language the variant, which is categorical the sum. Now
no, it's not. It's a discriminated union. It is not a sum. And it turns out that
your sum is categorical union. Because if you've got
No, it's
dollar
actually
and dollar,
not.
you
Talk
don't-
to Lisa. It is not a union. It's weird. It's something
Yeah.
very strange.
But isn't it not a sum then as well?
It's not. Well, I needed to call it something,
Yes.
and I needed to call it something that's kind of obvious what it is. And it needed to have a really short name because you end up writing it all over the place, because that's what you're returning, right?
Should it be a set?
No, because it's not a set.
No, it only got one. Only one at a time,
It
right?
holds only one at a time. It's a co-product. The set is a product. It's a weird product, but it's still a
And the
product.
size of is the biggest type.
Yes, the size of is the biggest type.
And it knows whom it's holding. And then it
Yeah, so like sum is a short name that's as close to what it is as what it is. And the thing is, type theory doesn't really have a name for this construction. Because when you do discriminated unions, or when you just do unions, you still, when you do a union of A union A, you still know you have two copies of A. And it turns out that doesn't work. Like you get...
The union flattens that.
No.
What you say is plus. So what you say is A plus A, then you know you have an A here, you have either an A from here or an A from here.
Yes, but the diagrams don't work unless you... Okay.
They are
Okay.
identical to A. Or isomorphic.
Yeah. This has to do with named categories with weird properties. It is not exactly the same. Yes, it's very close. We did, there's literally, unless somebody erased it, it's still on the whiteboard. On the other thing. So we have a proof that it's not the same thing, because you can turn them around and you get a different name for an isomorphic construct, and that's what allows you to screw everything up. Yeah. All right, so are we adjourned? Thank you very much. This was, yeah.